channel 2. So we kind of went through some of the basic things about the architecture yesterday. So I will draw my typical diagram that usually I draw. This is the system global area, which is SGA. Inside SGA we have a buffer cache. This is buffer cache. Then another major area that we have inside SGA is the shared pool, and inside shared pool we have quite a few areas. In fact, shared pool is such an important area inside the SGA that it has quite a few subcomponents, and we are focusing only on two subcomponents. The first one is the library cache and the second one is the dictionary cache, and along with that there are quite a few other ones, so we will not go into the details of them. So these are the two ones that we have seen yesterday. And then we saw yesterday that we saw the names. There are different processes, and the mandatory important processes are DBWR. This is called as a database writer. Then there is a process called as CKPT, which is called as checkpoint process. It's a program which is running. These are the programs which are running in the background. So those are called as processes. Then this is the LGWR, log writer. Then there are two more. One is PMON, which is the process monitor, and then there is one more called as SMON, which is the system monitor. So these are the 5 mandatory processes that are running on, and combined together the processes plus the SGA is called as the instance. That is what we saw yesterday. Instance has to be up and running in order for data to be accessed. So now this is my hard disk. On my hard disk I have at least 3 main types of files. One is the data files, then the control files, and then the redo files. So data files, we have seen data files are basically the table spaces. So in the table spaces, the first one, which is the mandatory system. The second, which is mandatory starting from 10G onward, is sysaux, system auxiliary. Then temp and undo. And then there could be so many other table spaces, and I'm not drawing data files here, I'm drawing table spaces. You can consider here that one table space is one data file when we start a database actually. Then I'm going to just draw a small line here to differentiate between the data file and the control file. There is going to be only one control file, but since the control file is so important, you can multiplex the control file and you can make 2 copies of the control file, or 3 copies or 4 copies. And usually it is always a good idea to keep the one copy of the control file on the C drive and another copy on the D drive, in one Unix partition, another one in another Unix partition. Why? Because if one partition fails, we still have another control file. So that is how usually the file layout is done. And then the redo, there are going to be 2 redo files. At least a database will have 2 redo files, and we will see why 2 redo files at least. The reason for that is very important. So redo files are at least 2, there can be more than 2 also. And redo files are also very important. They contain the information about each and every transaction that has happened in your database, and therefore the purpose of the redo is to do the recovery. If something goes wrong with your database, then you can use the information inside the redo. You can use the transaction information inside the redo, and then you can reconstruct or redo whatever was lost. And that is why redos are important from the recovery point of view. And since they are so important, again, if not as important as control file, but they are important from the recovery point of view, they are also multiplexed. So if this is the original redo, there will be a multiplexed copy of that redo, and if this is another original redo, this is the copy of that redo. So we'll talk about redos in a little more detail. So this is the basic and architectural diagram, and this part is called as a database. So now we fundamentally know the difference between a database and an instance. To access the information in the database, the instance has to be up and running. The command to start up the instance is startup, and command to shut down the instance is shutdown. So we'll run these commands inside SQL+. These are not Unix commands, these would be executed inside SQL+ once we log in. So this is our background. Now another process which is very important, which is the client process. Client could be anything, as we saw yesterday. SQL Plus is a client program. Then Toad, many of you must have used Toad or will be using Toad, tool for Oracle application developers. That is what Toad is. It is a web-based tool which works only on Windows machine. I will show you, if we go to our conference room, there is a Windows PC there. That's the only Windows PC we have, and we have Toad installed on that. So when a client program tries to access the data inside the database, it has to kind of connect to the server process. If there are 100 clients, there would be 100 server processes, and then these server processes are responsible for doing certain work. We saw that yesterday that they are responsible for doing work like parsing. They are responsible for reading data from the disk and bringing it into the buffer cache. All those things the server process are responsible for. And then what are the purposes of these guys? So we'll see now what are the functions of these processes, and we'll go further. So now yesterday we saw a select statement, how the select statement was executed. Now today we will see an update statement. We'll see an update statement. So here is my update statement. Update, the table is A, set ID is equal to 10, where ID is equal to 20. So initially the ID column was, I will do it the other way around. Initially it was 10, then we changed it to 20 for one of the columns in table A. So table A obviously is going to be sitting in one of the table spaces here. There is an extent of that table, and inside that extent there are blocks, and inside the blocks there are rows. So that table is there. Now how are things going to happen? The very first time this SQL Plus guy or the Toad client will execute this update statement, the statement will go to the server process. The server process is now responsible for doing the parsing. The first step of parsing we saw yesterday was the syntax check. The syntax check, so it will check, is this correct? Is this a correct update statement? And yes, it is a correct update statement, so syntax check will pass. Then the semantic check will happen. It will go and check, is the table A, does table A exist inside the database? How does it check that? Where does it check it from? Obviously the list of tables and views and everything else is stored inside the system table space in those data dictionary views. So there is again maybe one extent or two extents for that table which contains the list of all other tables, and that would be read from here and it will be brought into the data dictionary cache, which is part of the shared pool. So that will be brought over here if it is not there. So this is a very important kind of if the information that is required by the server process to do the parsing is not there already in the dictionary cache, then only the information will be brought from the disk and kept it into the buffer cache. So that will happen, the information will come over there, and then the maybe semantic check will finish, semantic check and all that stuff, it will also check the permissions and all that, and finally the execution plan will be generated by the optimizer. Optimizer is a set of programs, set of algorithms. Optimizer will generate that execution plan. Where will that execution plan be stored? The execution plan will be stored in the library cache. Now, before the optimizer is gonna generate the execution plan, optimizer is gonna check, does the execution plan of this select statement already exist in the library cache? If the execution plan of this select statement already exists in the library cache, optimizer will not do any work. Optimizer will say, I will just directly use that library cache's execution plan, and my job will be less, and I will go further, and then I will go to the next phase, which is the execution phase. So parsing will be finished, and then you will go to the next execution phase. Now about the execution phase. The execution has to happen. The first step of the execution is to bring the data of the table A from disk into the buffer cache if it is already not there. Same thing, if it is already not there. Assuming that it is not there, so let us say there are maybe 8 blocks inside this one extent, and those 8 blocks are brought over here. So I will just kind of make it a little bigger diagram. Okay, and maybe my buffer cache is also a little bigger. And these are the 8 blocks, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. These are the 8 blocks. Now once the data is brought into the buffer cache, then Oracle, the server process, will go and try to find out where is the row for ID equal to 10? Where is the row for ID equal to 10? So it is going to do what is called as a full table scan. It will read each and every block of that table, and somewhere it will find out, yes, in this block there is a row for ID 10, the value is 10, and it is there. It is one of the rows there. It is one of the rows over there. Now what Oracle is going to do, it has found that specific row. Just to update that one specific row, it will not just change one specific row, it will actually go and make the change from 10 to 20, but before it makes that change from 10 to 20, it will make a copy of that block. It will make a copy of that block for the rollback purpose, for the undo purposes. So that copy of block is made and it is kept inside the buffer cache. So original copy of that block is here, which is called as the undo buffer. And then the modified buffer, which is the new buffer, that is the data buffer. So this is the undo buffer, the original value, and the data buffer is actually the new value after the update. Why we have kept the undo buffer? For our rollback. So this is what happens. It is the copy of the entire block is made. Now one thing to understand here in Oracle, that if I want to change one row, or if I want to read one row from which is in block number 29 of extent number 28, whatever, then that entire block is read from the disk and brought it into the buffer cache, just for that one row. Oracle will never ever just read that one row and bring it into the buffer cache. The I/O, the input output that happens, the reading from the disk and bring it into the buffer cache, and then writing from the buffer cache back to the disk, all this stuff is called as I/O, input output. All this I/O happens in terms of blocks. So therefore we may need just one small row, but the size of the block is, let us say, 8K. We have to read 8K, bring it into the buffer cache just for that one row. If the size of the block is 16K, we have to still read the entire 16K and bring it into the buffer cache. And therefore you will see, just having a bigger size of data block is kind of a bad thing. If my block size is 32 kilobytes, then I need only one row. Select star from employees where name is equal to Shaker. I need only one row because let us say there is only one row with the employee name Shaker. Then for that I have to read the entire block maybe, in which the row is sitting there. So this is kind of a wrong thing, or this is kind of a bad thing from the performance tuning point of view, that if we need only small amount of data, and for that we have to read huge amount of data blocks. And therefore if your users are going to write queries which will be fetching only small amount of data, this is very important to understand. If your users are going to write queries which will be fetching only small amount of data, then it is not a good idea to have a bigger block size. Then it is not a good idea to have a bigger block size. But if your users are going to write queries like this, select sum of salary from employees, sum of salary, it will give only one number, but to get that sum it has to read each and every block, each and every row inside the block. So if they are going to write this kind of a query, sum, count, aggregation functions, so this is what is called as a OLAP type of a query. So OLAP, online analytical processing, OLAP, OLAP and OLTP. So if you are doing sum, count, group by and all those things, you will be reading a huge amount of data, and those type of queries are called as online analytical processing kind of queries, OLAP queries. And then as opposed to that, if you need only some small amount of data, for example, if you go to if you call somebody on a call center of, let's say, Reliance, and you tell them that my mobile telephone number is this and my telephone bill is incorrect. So they are going to get only information about you from their entire huge customer database. So this is a smaller fetch. Out of 1 million customers that they may have, they will be fetching only information for one customer, and this kind of a query is OLTP query. Online transaction processing, OLTP. Online transaction processing query. So database is the same, but the purpose of the database could change depending on what type of queries are written. So some people will say, oh, we have an OLTP database. That means you are usually, not always, usually the type of queries that you will be writing are going to give you smaller amount of data. Some people will say that we have OLAP database. So therefore, before you create the database, the DBA has to decide what is going to be the size of the block. What is going to be the size of the DB block? and that decision has to be made before the database is created, and at that time you must go and ask your business users what type of queries are you going to write. Are you going to write OLTP kind of queries or OLAP kind of queries? And depending on that, you can go with the bigger block size or the smaller block size. And since many times we cannot figure out, some people will say no, we will write both kind of queries, then in that case go with the medium, which is the 8K block size. And that is why the default is 8K. You can start from 2K, 4K, 8K, 16, 32. You have a huge OLAP kind of a query, then go with the higher block size, 32K. And this is what is called as Decision Support System, DSS, or this is what data warehousing is. So if your database is a data warehousing database, then use a higher block size. If it is OLTP, then use a smaller block size of 2K. Performance will definitely improve depending on what type of queries are written and what type of blocks you have. So that was a discussion about the block. Now, once we know that my block size should be, let us say, 2K, how to set that up, we will see that next time. But that is the concept about what should be the block size. So now, coming back to our update statement. The update statement, the server process has brought the data blocks from here into the buffer cache, and then it has identified the block which contains the row for ID is equal to 10, and then after that it has made the copy of that before updating that copy. So this is that undo copy or the undo buffer, and this is actually the data buffer. The user has still not committed it. The user has still not committed the transaction. So this is a very important information. This is very important information. Now we had seen yesterday or in our previous discussion that the undo should be written to the undo table space. What is it doing in the buffer? Now, Oracle is kind of a the design is like this, that everything has to be brought into the memory. Everything has to be brought into the memory inside buffer cache. Blocks would be here, other things would be here, and then it is served to the client. Then it is served to the customer, you can say. So always data would come from here to here, and since it comes from here to here, it will also go from here to here. So the moment this space, the moment the buffer cache is not big enough to hold all of your undo buffers as well as your data buffers, then what will happen? Then the data will be written by the process dbwr to the undo or to the actual data blocks. So the only time when this is actually not big enough to hold the data, things will be written back to the disk. If this is big enough to hold the data, things will not be written back to the disk. So I want to make a very important point to understand here, that when I update certain things, I will have a before image of that block, which is called as the undo block, and also the after image of that block. After means after the modification, before the modification. So after image, image of that block, which is the undo. And now this undo will remain there for how long? Until you either type the commit or roll back. If you type the commit, then this will be marked as the expired block, which is not required anymore. Will the data 10 when that block go away? No, data of 10 will remain there, but the block will be marked as expired. Now, if let us say, if I say commit, the moment I say commit, many people have a notion that data is safe now. Obviously data is safe. Many people have the commit that data is written to the disk, but it is not written to the disk. The data is not written to the disk the moment you type the commit command. The moment you type the commit command, this is marked as expired, but there is a lot of space still here which can hold that modified block, and therefore the block which is there on my data file still is the old block which contains the value of 10, and the modified and committed data is in my buffer cache. So my statement is this, that situations may arise that the committed data will still be in the buffer cache but not written to the disk. Let me say that the committed data will be in the buffer cache but will not be written to the disk. That kind of a situation may arise. Which process now is responsible for writing data from buffer cache and putting it into the data files, respective data files? It is the DBWR process. When does the DBWR process does that? Whenever it finds time. There is a certain specific interval by which after that interval DBWR will wake up and it will write the data from here to here. But that will never happen just when we type a commit command. That is an important point to understand. So committed data, in other words, committed data may not be written to the disk immediately. It will be written to the disk but not immediately. So there is now a problem that we are going to discuss. The committed data is now here but not here, and at this time the electricity goes off, assuming that there is no UPS, hypothetical situation, and suddenly your machine crashes. What happens now? The user thought that he has done a commit, and actually he has done a commit, and on the disk still the old data is there. So that is where our redo kind of comes into the picture. So this is where I'm going to introduce another area. This is called as a redo buffer, redo log buffer, redo log buffer. So what is the purpose of this? The moment an update statement, let us say any kind of DML, DDL is written, not SQL, not just a select statement. Select statement does not change any data. So anything that changes the data, anything that makes any changes to our database, and create will make change to my database, the alter, the drop, the truncate, the insert, the update, delete, all these things will change, will make changes to my database. Select statement will not make any change. So select is not considered in this. So any of these statements are written to what is called as a redo log buffer. This is the area inside the memory where the update, the insert, the delete, the create, the drop, all those are written over here, along with certain other information. What time was that? You know, what is the SCN number? Basically, I should say the SCN number. We saw yesterday, SCN number is kind of a timestamp. It's a number, but it is kind of a timestamp when a specific thing happens. So at what time, that means at what SCN I executed the update statement. Second thing, is the update statement committed or not? So commits and all those things will be actually recorded in the redo log buffer, which is the area inside the memory. And SCN number is the most important thing over there, because we know that the first thing that was done was the update, the second thing that was done. So the SCN number is just a number. So let us say there is 41. So at the time 41, update statement happened. Then 42, some other insert statement happened. Then 45, then the commit happened. All those things are recorded inside the redo log buffer. All those things are recorded inside the redo log buffer. Which things? Anything apart from select. Anything apart from select. Those are recorded into the redo log buffer. And then what exactly happens when we type the command commit? When we type the command commit, the transaction, the update transaction, that is suddenly written from here by the process of LGWR to a file called as a redo file. Redo log buffer. So there is a buffer, there is a file, there is a buffer, there are files. So if to a file this information is written, and it is written sequentially, that means one after another, one after another. Here it is not sequential, here it is random, because first I may update the table A, and DBWR will have to make changes to table A, which is over here. Then I may update the table B, and DBWR will have to make changes to table B, which could be in a totally different data file. That is why this is not called as a sequential write. This is a random kind of a scattered write. And here on the redo side, you will hear this phrase a lot of times, that the writing to the redo file is in a sequential manner. That means it is written into one file, one after another. The update, the insert, the update, the delete, and all that stuff. So all this information, the actual statement itself, the SCN number, the commit information, and all that stuff, all this clubbed together is called as a redo vector. Redo vector, the information which is required later on when something goes wrong. That we are going to get this information from the redo vector, and we are going to rerun the insert statement. We are going to rerun the update statement, and by rerunning the update statement or insert statement, we are actually fabricating the data which was fabricated earlier. Vector is not, I mean, yeah, you could, in that situation, if you see that, yeah, it's kind of in a mathematical way, yeah. But redo vector is basically an information which is inside the redo log buffer that will be helpful to us, when we do the recovery. So that's, I think that is probably the basic thing that you can remember. The information which is going to be helpful during the recovery. That is what the redo vector is. So now what happens when I fire the update command? The data, the parsing and all those things will happen. Okay. So let me again start from the very beginning. I know I'm repeating this thing again and again, but let me start from the beginning. The client connects to the Oracle database. For that client, a special process is started called as a dedicated server process. When the client types the exit command, the dedicated process dies off. That is why it is a dedicated process. Then client actually, first thing that will happen is the authentication. The very first time you are going to do, put the login ID password, the authentication is done by the dedicated server process. It will go and check, in the system table space, db_users. Is there a user called as Shaker? What is the password of that user? And that will be done by the server process, and that is called as the authentication process. So user is authenticated by the dedicated server process. Once the user, and with the help of dictionary cache. Obviously, in the system table space, there is data dictionary that will be brought into the buffer cache. If it is not buffer cache, that will be brought into the dictionary cache if it is not already there, and then the authentication will happen. After the authentication, user fires a command, update a set ID is equal to 20 where ID is equal to 10. Then the sudden first thing will start with parsing. I'm not going to go into the details of parsing now. The syntax check will happen, semantic check will happen, execution plan will be generated if it is not there, and then execution plan will be stored into the library cache for future purposes for somebody else who might be executing the same thing, and then actually the execution will start. The execution will say, is the data that I require already in the buffer cache? If it is not there, it will be brought by the dedicated server process from the appropriate data files. All those blocks which are required will be brought into the buffer cache. Then one of the blocks contains the data that I need to be updated. And then the original copy of that data is kept somewhere else, and that original copy is called as a undo buffer. And then the main copy is modified with the new data. The main copy is modified with the new data. This copy will remain in the buffer cache till what time? Till the time that some other person, let us say the update statement was executed by Toad, some other guy came in and he executed just a simple select statement. Select star from some very huge table, and that huge table is sitting in this in this data file. So this very huge table contains 1 million blocks, or let us say 1,000 blocks, simple thing. 1,000 blocks will be read by the dedicated server process of this client, and they will be brought into the buffer cache. Now obviously buffer cache is not big enough to hold 1,000 blocks, let us say. Then what will happen? Then these blocks, even this, any of the blocks, which are actually modified. Not all the blocks should be written down to the disk. Only those blocks which are important for modification. So in this case, this block and this block, they will be written down to the disk by the dbwr process. This block is the undo buffer, will go to the undo table space. This block is the data buffer, will go to the appropriate data file. And then the remaining blocks that are required by the server process of another client will be brought into the buffer cache. So this is basically what that LRU mechanism is. Least recently used blocks, that means older blocks, little older, are now are pushed out of the buffer cache. That is the LRU mechanism. So again, second point now which I want to emphasize on, that data which is not committed yet, may be written to the disk. Correct? Why? Because some other guy required space in the buffer cache. So I am going to write these 2 points here. Number one, committed data may not be written to the disk. In fact, may not be written to the data files, okay, but it is written to the redo, but it is written to redo file on the disk.
Through database writer only?
No, through LGWR. Anything from here to here will be done by LGWR. Anything from buffer cache to the data files will be done by DBWR.
And DBWR and LGWR? time dependent or memory dependent?
They are memory dependent and time dependent, both. That means after certain time they will be flushing information from memory into their respective files at certain time.
RLB and BCs contain the enough space. Still they...
No, then there is no need. They will check after certain time, certain interval, is there any need to write certain things from here to here. If there is no need, then it will not write anything. It will unnecessarily not generate the IO. So if it finds that there is a need to write 2 blocks to the disk, then it will write them.
Need is only when we need memory space, right?
Need is only when we need memory spaces, and need is, usually it is also time dependent. So need dependent and time dependent. Every 3 seconds, it will write those things to the disk. So, and what is written to the disk? That is also important. A term there, what is written to the disk? The term is called as dirty block. What is a dirty block? A block that has been modified by somebody, but it is not written to the disk, is a dirty block. And only dirty blocks are written to the disk. Not everything from here goes back to the disk. LGWR does the same thing. LGWR is dependent on 3 things. It is dependent on time. Every 3 to 4 seconds it is writing things from the redo log buffer to the redo log file. Then it will also write, 3 seconds seems like a very small time for a human being, but within 3 seconds Oracle can load around 1 million rows there. So if the redo log buffer is full even before that 3 seconds, then also LGWR will write things to the disk. So if it is full or 1/3 full, I think there are different algorithms there. If it is 1/3 full, it will be writing to the disk. If it is 1 MB or 1/3 also, I think one of those things. Yeah. So there are multiple things that if it is 1 MB full, then it will write. If it is 1/3 full, it will write, and every 3 seconds it will write. And after commit, that is what I want to say. That commit is very important. So when some transaction is committed, I am guaranteed by Oracle with the help of LGWR that the redo vector of that transaction is written to the redo file. The redo vector of that transaction is written to the redo file. That is 100% sure. And when the data, when I say data, I'm saying redo vector. When the redo vector is written to the disk, that means my data is safe. Is my actual data on the disk? It may not be on the disk, or it may be on the disk, I don't care. But I am guaranteed that my redo vector for my transaction that I have committed is written to the disk, where disk is redo log file. And since I am guaranteed over there, if something goes wrong now, the actual data is not written from here to the disk, the redo vector for that transaction is written to the disk, and at that time, as I said, the power goes off. And suddenly, when the power goes off, the instance crashes. That means our memory is wiped out, our processes crash. What remains there is the data on the disk. Data on the disk will always stay there. So now what is on the disk? On the disk, I still have the old value, 10, because it was not written to the disk. But it was committed. So what happens now? Oracle is smart enough to know that when next time I start up the database using the startup command, it will go and check in the redo file, is there any transaction that has been committed but not written to the disk by DBWR. It will know that internally, how, and we will see that thing a little later. Then it will redo that transaction. That means it will replay that transaction, and by replaying that transaction, that 10 will get changed to 20. The 10 will get changed to 20. So this is this is the functionality of redo log buffer and LGWR. So these 2 things are kind of important. Okay, so we'll kind of